So we'll discuss tensor products today, tensor products of Hilbert spaces and tensor products of operators on Hilbert spaces. So which will define tensor product of Neumann algebras also, in a sense. So before further, we need the following tools. You take any set, and you have a function. This is called kernel or something. Such that then K is said to be positive definite kernel. This is called kernel. Okay, this function is called kernel, positive definite kernel. If for all x1 up to xn, for any x1 up to xn in S, the matrix take this matrix xi is j in ij. Okay? This is positive. This matrix is positive. That makes sense. So, which is equivalent to saying, this equivalent to saying, for all C1 up to Cn, constants in C, this K, I mean, you call this as C bar. C bar for all C bar equal to this. We have to know that K as a matrix, you call that as K for, I mean, for the time being. It depends on x1 up to xn. So this K, C bar should be greater than or equal to 0. Okay, for all C bar, right? That's what it means for all C bar. This is what it means. And if you just expand, that will just say that CH, CJ bar, CXI, XK is greater than or equal to 0. Point n. So this matrix is in Mn, and this should be positive definite for all n. If given any x1 up to xn, this should be positive definite. So this should be greater than 0 for all C1 up to Cn in C, for all x1 up to xn in X, S, and for all n, of course. So this is what is called a positive definite kernel. So if we have a positive definite kernel, we can construct a Hilbert space corresponding to that. Okay, that is what this following theorem says. This is usually called as Kolmogorov construction or Gelfand construction. Doesn't matter. Okay, you can call one of them Kolmogorov. He is a probabilist, and Gelfand, who is a functional analysis. Okay. So whichever you want. Okay. This is very similar to Gelfand-Neumann construction. So that's why. So for K from S cross S to C, the positive definite kernel, okay, there exists a Hilbert space H and a function lambda from S to H, okay, such that lambda S lambda T equal to K H. So this is the existence. Given a kernel, you can construct a Hilbert space, and there is a uniqueness part of it. I mean, so given a positive definite kernel on a set, you can construct, the set is not a vector space or something, it's just a set. Okay, so you can construct a Hilbert space H where you can embed this set such that this positive definite kernel can be, you can get back the positive definite as the inner product. And this set is total. Okay, and lambda of S, I mean, that's very important, contained in H is total. That is span closure of lambda s is everything. So further, there is a uniqueness condition. Further, if you have some other further, if there exists a h prime and lambda prime from s to h prime, such that it satisfies the same condition. Lambda prime of s contained in h prime is total, and lambda prime of s, I mean, when it's clear, it will be unique. We have already done this just for the equal to kst. It's clear what you would do. Okay, then there exists a unitary u from h to h prime such that u of lambda of s will go to lambda prime s. The uniqueness part is clear. We have done it several times. You just have to define it as lambda is going to lambda s prime. Just define it. And by this relation, it has to preserve the inner product. Then you can extend to the span closure by as a unitary. That we have already seen several times. So uniqueness is clear. Just a statement. So only the construction we have to go through. So if you take any Hilbert space, first notice that if you have inner product, okay, then if you have any, I mean, if you have, suppose if you have on a Hilbert space, suppose if you have a kxy is just the inner product xy, then it is clear that summation lambda I, lambda j bar, xi, xj bar, xj, xi, xj, the this product. Okay, I mean, this is just, I will erase it. This is greater than or equal to 0 because this is just equal to, you can take the summation over ij, that the summation is also over I and j, both of it. No. S is any set. Here I am sorry, this is I and j. I and j equal to 1 to 1. The summation is between I and j. Okay. Yes. Okay. And there is nothing countable about it. This is finite sum, of course. So if you take any inner product, you take any such sum, then this is just equal to inner product of summation lambda I xi, inner product of summation lambda j xj. I mean, the same thing. Maybe you can put I, doesn't matter. It's different summation. And this is, of course, norm of this. Norm of whatever you have square, which is greater than or equal to 0. Okay, so it is this property we have just generalized for a kxy. Okay. So any inner product function is a positive definite function. So as you can see, we can construct strip f equal to all those functions from S to. So you take all functions such that f of s equal to 0 except finitely many. It is non-zero only in finitely many places. Okay, or f of s not equal to 0. F of s not equal to 0 for finitely many. Okay. Okay. Then define, it's just a bracket kind of thing, f and g, this function equal to summation. You sum over both s and t, f of s, g of t. I think we need a bar times kst. Okay, because it's a finite, f is finitely many, non-zero, finitely many places, g is also finitely many non-zero places. The sum will be finitely many, finite sum. Okay, this is the finite sum. So this is well defined. And this is a semi-inner product on this, right? This is linear in the first variable, anti-linear in the second variable. And if you have no. Yeah, if you have f and f of s, f of t bar, Yeah. Then if you have, I mean, if you have fs f of t bar, then positive definite will say that this is greater than or equal to 0. So this is a, ff is greater than or equal to 0. It is anti-linear and all that. Ff is greater than 0 thanks to positive definite. Okay. Okay. So now you can let n equal to, the same construction, n equal to all those f in L or f such that f of equals 0. Okay. And semi-inner product is also continuous because it will satisfy the Cauchy-Schwarz inequality. Continuity of the inner product follows from Cauchy-Schwarz inequality, and semi-inner product is also continuous. Okay, you can verify because the Cauchy-Schwarz inequality will be satisfied. Since we already gone through GNS, and we'll just quickly go through the points. Okay, now so n is closed. N contains, the semi-inner product will give you a topology on that. You can worry about all that, or just vector space quotient you can say. Okay, you don't need to take all this closure to consider S in N. It doesn't matter. You don't need to take closure because we are not going to consider norm space or something. We don't need to worry about N is closed or something. Sorry, you can forget. That's not needed. It will be if you take the topology generated by the semi-inner product, then it will be closed, but doesn't. We don't need that. We are just taking this vector space and this vector subspace and taking the quotient. You call this as H naught. Okay. Then define f plus n, g plus n equal to fg. Okay. This will be positive and all that will be clear, but this is well defined due to Cauchy-Schwarz. We have already done this for GNS construction, so I am not going through this. So you can see. Okay. You only have to verify that f plus n and some g plus, with some n is 0. Okay. This is 0. That will follow because of Cauchy-Schwarz. This will have norm of this, norm of this, then norm of this, norm of this is 0. So because of that, it will follow. Okay. So thanks to Cauchy-Schwarz, this is well defined. And this will be an inner product on this. Okay. So this is an inner, maybe I call it not. This is equal, sorry. Here is bracket, I'm sorry. This is bracket and that is not. So this is inner product on H naught and complete. You get H inner product. You extend this inner product and you get a completion. You take the completion of this. Yeah, if you complete inner product space, you get an inner product space. The inner product will extend. So this is it. Okay. Now, how will you embed this lambda S? Okay. So for S in S, define lambda S to be the delta function, delta S, where delta S of t equal to delta S t equal. And delta S is 1 at the S place, everywhere else it's 0. It is that function. Then it is clear that lambda S, lambda t, if you take that, that is just going to be summation of lambda S at L times lambda t at Tm, K Lm, and that will be non-zero only at Lm, which is equal to Ksg at first. Clear? Okay. Summation over L and M increases this. So everything in the proposition is satisfied, and it's also clearly the uniqueness is also satisfied. So it's clear the theorem is proved. Okay. So we want to use this. If you want to define tensor product, you can just you take H1, Hilbert space, and H2, another Hilbert space. Okay. Then you can take the maybe filter, whatever, I don't know. You can just take, you can talk about, just formally, you can take H1 tensor H2, just formally, you take H1 tensor H2. But this will not be enough. So you take maybe on the top, I. Then you take the summation, take formally summation, because this will not be a vector space. I mean, if you take something like this, then the sum, so you have to take summation lambda I xi1 tensor xi2 to take formally these kind of things. Okay. Then you take another mu I, summation mu I, some yi1 tensor yi2, and define the, I mean, or you can just worry about this, just this. You define the inner product to be just xi, yi, x1, x2, y1, y2. When x1, x2 times y1, y2. You just take the product. Okay. You define the inner product between this x1 tensor x2, y1 tensor y2 to be this. Then you extend it linearly. You can take formal linear sum of this, just formal linear sum of this. That will give an inner product on some space, but there will be a semi-inner product. You have to quotient it and do all that. But then you have to identify many things. You have to identify something which will all follow if you use this construction. Okay. So what we do is the following. So define. So H1, H2, 2 in Hilbert cases. Define lambda k from H1 cross H2 to C by not H1 cross H2. I mean, the function is, our S is H1 cross H2. So K should be from H1 cross H2. I mean, cross H1 cross H2. Right? That is how it should be. Our K is H1 cross H2. Sorry, our S is H1 cross H2. Okay, so S cross S it should be. Okay. So this is K of any x1, x2, comma y1, y2 equal to just the product of x1, x2, the product of n of y1. Okay. So we need the following lemma, which is well known. I will orally tell you a proof for you. Okay. The proof is, if you have a B or positive definite matrix, okay, then you define, there is something called Schur product, Hadamard product, you know that? The entry-wise product. Matrix-wise product is, there's a commutative product on this matrix. Just make entry-wise product. Okay. Now you define, maybe I need a different answer. A, B, maybe A, B at Ij equal to just Aij, Bij. That's all. Okay. Then this is also positive. This matrix is also positive. This is n cross n matrix. This is also positive. So there may be A, B, or N, M. Okay. So this is a well-known lemma. If you want a proof, see, the easiest proof is through probability. Okay. You take, you know measure theory anyway. So you can take two independent random variable, n-dimensional random variable. Okay. Xi equal to xi1 up to xn. Okay. This is a random variable, and eta equal to eta1 up to eta n. Complex, because we are dealing with complex, you take complex random variable. With mean 0, I mean, tuple, n-dimensional random variable. Random variable is just a measurable function from that. And then the expectation is just the integration over that. So expectation is 0. Okay. So that is what usually denoted by Ez equal to 0. 0 vector. And E eta equal to 0. These two are independent. You can construct any independent random variable given any distribution, because if you distribution is just the measure which is determined by the random variable. Okay. So if you have a random variable with some distribution, so you have a measure and it's just a measurable function. You have a measure, the random variable will give rise to another measure. That is what is called distribution. I mean, if you have a measurable function from something to omega to C, on C, this will give a distribution, right? If you have a mu on this, then mu F inverse will give a measure on this, right? You know this, no? So that measure on C is called the distribution of this. Okay. So if you have normal random variable, you take normal random variable. Normal random variable, it is just normal random variable Gaussian. You must, normal random variable is just you take. Let me go through one by one. The proof of this is follows. I mean, I will just make the points. You take, let A1, AI is a normal random variable with 0 mean and standard deviation, variance 1. This just means that it has density e power minus t square 1 by root 2 6. 1 by root 2? 1 by root 2, I think. I'm t square by 2. I think 1 by root 2, I think. I mean, you have to get the integral 1. So for that 1 by root 2 is needed. 1 by root 2 sigma. Okay. So this is, if you take this is the density. Once you know the density, you can integrate it on some any set and you get the measure of that set. That is how the density is defined. This is a Radon-Nikodym derivative with respect to Lebesgue measure. Normal distribution is a measure, and that measure, this gives this. So if a random variable is a function defined on somewhere, you don't, when you talk about random variable, you need not talk about the measure space. I mean, it has the distribution is enough. Okay? Some measure space is somewhere. Okay. When you talk about collection of random variables, all should be defined on some measure space. Okay. So random variable just a measurable function to real line or complex plane. If you say complex random variable, it is complex plane. Okay. So it's a normal random variable. Density is given by this. This density gives a measure, and that is the distribution given by this. So the measure is somewhere. This is defined on some measure space, but that will induce a measure on this. That induced measure by this random variable is this normal random variable. So you have AI, which are some random variable, independent random variables. Independent means E of the integral of AI and integral of AJ is integral of AI, AJ, the product. Okay? That is what independence means. Okay? So if you have a random variable A1, maybe 2n, A1 up to AN, B1 up to BN, okay? Then you define a random variable AI plus IBI. Okay? You call this as CI. This is a complex random variable. This complex random variable Ci will have a covariance matrix. And this will also have mean 0 because each A has mean 0, BA has mean 0. Okay. Now you take our, if A is positive definite, A is equal to some C star C, right? Where C is self-adjoint. Okay. Then you take, this is Ci of the term. So this small Ci, okay? Small Ci. Small c, okay, the small c. If the c acting on the small c, okay, will give you a random variable, some other random variable, gamma I. That gamma I will have the mean 0 again. That will also have, because it's just a linear transformation. 0 will be taken to 0. It will have mean 0. And the covariance matrix is, if you take some AI, xi, I mean, if you have any xi, a vector, the covariance matrix is this EI, Xi, Xi. Okay? This integral. This is Xi J bar, maybe, if it is complex. Okay? So this is what is the covariance matrix. So given any positive definite matrix, you can find a Gaussian random variable, n random variable, whose covariance matrix is that positive definite. Okay. Now, if you take two Gaussian random variables, which are independent, okay, so Xi is a Gaussian random variable which follows 0, normal 0 under a matrix A. Okay, not Xi, Xi1, Xi equal to Xi1 up to Xin, and another one is eta equal to eta1 up to eta n. This also follows normal 0b. Okay. Then the product of the random point-wise product of this, okay, Xi eta equal to this Xi I eta I. Okay. This product, point-wise product of this random variable, that will follow this 0 A. Okay. This you can verify. That's because I know this should be independent. Xi and eta is independent. Okay. That is because E of xi I, xi j bar, eta I, eta j bar. Because of independence, this will be equal to E of xi I, xi j bar, eta I, eta j bar. Okay. Because of this, because of this independence, the product random variable will have covariance matrix Schur product, the Hadamard product. Because of that, it will follow that if A and B are positive definite, A Schur product, Hadamard product is also positive definite. Okay. So this is a general theorem which uses, you can use probability. So this is a standard theorem. Okay, I just want to orally give you the proof. I will erase because I haven't written anything in detail. Huh? Huh? It satisfies that condition. You take the K of Xi Sj, it's a positive definite matrix.
For all Xi.
For all Xi. Yeah, for all Xi. So the product, Hadamard product of two positive definite matrix is positive definite. Of course, the product of two positive definite matrix is not a positive definite. Of course, it's not even self-adjoint. Ordinary product. Okay, because it need not be even self-adjoint. Okay, so unless they commute. So from that it follows, why I say is from that it follows that this K is positive definite. Okay. I mean, I did all that to prove this. So if you have two Hilbert space, then you can, because inner product is positive definite. Inner product is a positive definite function. Okay, on H. If you have H is, if you treat any Hilbert space as a H as a set, and if you define the inner product as the K, then that is a positive definite. So if you take the product, pointwise product, that gives a positive definite function on H1 cross H2. Now the corresponding Hilbert space is H1 tensor H2. That's all. You have a positive definite function on this that gives a Hilbert space. That Hilbert space is H1 tensor H2. On this, you have this on this H1 tensor cross H2 as a set, to call it S or something. This is contained in H1 tensor H2 as a total set. So that if you have this X1, X2, okay, you denote that as H1 tensor X2. This is embedded here through that, I mean, in a unique way, of course. Okay. That is X1 tensor X2. So now span of this, it will be like summation lambda I xi, maybe xi1 tensor xi2, right? Span of this. And this will be dense there. So you take formal tensor will be, I mean, this is formal tensor, it will be dense. So without ambiguity, we can denote this X1 tensor X2. And you will see these are all exercises you have to do. I will not do each and everything. So because this has an inner product, that will give you a norm. Okay. And if you take the difference between these two things, if you have a lambda X1 here, and if you have a lambda, this will be equal because we are quotienting with respect to the inner product. No, you take this minus this, take the norm square, that will give you the inner, you write it in terms of inner product, that will be 0, right? You take this minus this, okay? Take the norm square, that will give you an inner product. I mean, that has an inner product given by that positive definite function K, okay? That will be 0. So these two should be equal. Similarly, if you have a lambda here, you can take it down. So you can just put a lambda here outside unambiguously. You can write it lambda here, lambda here. Similarly, you can keep one of them and sum in the other tensor. Similarly, you can keep this, I mean, fix this and sum of that. What I mean is X tensor y1 plus y2 equal to X tensor y plus X tensor y2. Because you compute the inner, I mean, you take this minus this. You can compute the inner product, do the exercise, it will be 0. Okay. So if the inner product is 0, these are all elements in the H1 tensor H2, and they are equal. Okay. So this is multilinear. This tensor is a multilinear function. So is there any other property? You can add some, you can do this, you can take the scalar. So we will see. Okay. I mean, all this obvious property you can verify by using this trick. Okay, each and everything. So that is exercise. So this is how the tensor product of two Hilbert spaces is defined. So we will, I mean, this is another exercise. which will be clear. So if we have S1 contained in H1 and S2 contained in H2, okay, maybe exercise or proposition. I will tell you the proof anyway. Then S1 tensor S2, which is all those xi, x tensor y, where x is in S1, y is in S2. Okay. These are total. If you have two subsets which are total in H1 and H2, then this contained in H1 tensor H2 is total. So why is this? This is total means summation lambda I, those kind of xi that is dense there, and summation mu I something is dense here. And you want to get, so to show that S1 tensor S2 is total, you have to get all the elementary tensor here. That's what you have to do. Then that is dense here. And you see that this is a continuous function. I mean, this is xi. If you have some xn tensor y, this will converge to summation x tensor y if xn converges to x. Use the inner product and all that, it will follow. Similarly, you can put a yn here. So from these things, you can generate all this the elementary tensor from, the linear combination of elementary tensor from here. And so you will get if you take the span of the closure of this, that will give everything. So this is an exercise. Okay. So this is clear. So this in particular, corollary to this is if EI contained in H1 and Fj contained in H2 are orthonormal basis, then this EI tensor Fj, okay, with Ij, Ij running over I equal to 1, 2, maybe you consider, you assume that they are infinite dimension and j equal to 1 to infinity. These are orthonormal basis. Then you vary I and j from 1 to infinity, EI tensor Ej. That is orthonormal basis. These are orthonormal basis. You can check the orthonormality, orthogonality. Normality is clear because the norm will be multiplication of the norm, so it will be 1. And orthogonality is clear because you take the inner product, which is just the product. EI tensor Ej, EI tensor Fj. EI tensor Fj. And if I take two of them, EI1 Fj1, EI2 Fj2, we take the inner product, it will be 0 unless both of them are 0. So another thing is totality is the only thing you have to check. That follows from this. This is a total set, this is a total set, this should be a total set. So from this it follows that this is a orthonormal basis. So that's one thing. So this implies one more thing, that if corollary is if H1, H2, our positive definite kernel does not guarantee any separability or anything. Okay, that we have to work with the Hilbert space. Okay, so if H1, H2 are separable, then H1 tensor H2 is also separable because it has a countable orthonormal basis, right? So it's also separable. So if you tensor to separable Hilbert space, you are going to get a separable Hilbert space. So you are not going to get anything different. Right? It's an isomorph. If it is finite dimensional, you can verify that Cn tensor Cm is isomorphic to Cnn, okay, the product. If you take direct sum, the dimension will sum up. This is like a product. Cn tensor Cm is Cn. The product, the dimension will be the product n diam. So, but in infinite dimensional, there is no difference. It's the same Hilbert space. Same means it is again a separable Hilbert space, which is isomorphic to H1, both H1 and H2. But why we do that is this is a different this is a different avatar of this, right? This is for example, we can define operators, we can do something. It is for that purpose we define the tensor product. This is just a different representation of the Hilbert space. Whatever you want to call it, different avatar of this, different incarnation. It's the same Hilbert space. In a sense, they are isomorphic, they are all isomorphic. But why do we define this is, for example, we will define operator. It is for our mathematical purpose, we define it like that. It is not going to give a different Hilbert space. So, okay, so now we have to define operator, okay, for position. If T is in B of H1 and T1 is B of H1, T2 is in B of H2, okay, then define T1 tensor T2 as T1, X1 tensor X2 as Tx1 tensor Tx2, okay, which is of course well defined, okay. This is extends linearly on the span. Okay. They extend linearly on the span, elementary tensors, finite tensors. Okay. Now this is bounded on the span on finite tensor. Okay. I mean, a tensor Hilbert space, H2 tensor H2, you take the elementary tensor like xi tensor y or x1 tensor x2, you take the span and it is a closure of that. Okay. It's not like linear, I mean, direct sum. Direct sum, you take anything can be written as x direct sum y. Here it's not like that. Okay. So you have to take the elementary, I mean, like elementary direct sum. Everything is elementary direct sum, x direct sum y. Here it's not like that. You have to take the elementary and take the span and take the closure, because that's a mistake one may make when you work with that. Okay. So you have to show that this is bounded on the linear span. See, usually when you want to check unitarity, it is enough if it is preserves the inner product and a total set. Then you can extend to the linear span and but when you want to check boundedness, you have to check it on the linear combination, because it may be bounded on this but may not be on the linear combination. Okay, that problem may arise. So you have to check it on the linear combination. So T1 tensor T2 is bounded on the finite tensor. This is the claim of the proposition. Okay, so with, I mean, you can define on any vector space. It need not be a Hilbert space, just an inner product space. T1 tensor T2 equal to norm T1 tensor norm T2. Okay. I mean, this is just maybe you put a tilde here, okay, because this is only defined on the finite tensor. So now it is a bounded operator on a dense subspace, so you can extend it. Okay. So now T1 tensor T2 is the extension to Hilbert space, H1 tensor H2. This one, whatever I have defined here, okay, this is a bounded operator on a dense subspace, so it extends to the same norm, okay, with norm T1 times norm. It's just the product of the norms. Okay, T1 tensor T2, the norm is product of the norm. Okay. So first we verify this for finite dimension. Okay. The idea is we verify for finite dimension, and you can see that whatever the computation we do, it only requires finitely many vectors. So proof. So if H1 tensor H2, H2 are finite dimensional, and T1, T2 are self-adjoint, normal is okay, but self-adjoint is fine. Self-adjoint. Okay. Spectral theorem, finite dimensional spectral theorem says that they have eigen values, eigen vectors. So let EI I equal to 1 to n contained in H1, Fj j equal to 1 to m contained in H2, eigen vectors for T1, T2 with eigen values, lambda I, mu j. Okay. Then you can see that EI tensor Fj, then EI tensor Fj, eigenvectors with eigenvalues. Lambda I, the product lambda I. Okay. That's clear, no? T1 tensor T2. EAG vector eigenvalue for T1 tensor T2. So if, I mean, EAs are orthogonal basis. Eigenvectors will form an orthogonal basis for a self-adjoint operator. So similarly, Fj. So EA tensor Fj, that will form that's an orthogonal basis for H1 tensor H2, and they are exactly eigenvalues for whatever you are going to define as T1 tensor T2. And the norm of some operator is the maximum of the eigenvalue. You know that? That's clear? Clear. Okay. So norm of the vector is maximum of the eigenvalue. So maximum of the modulus of the eigenvalue. So maximum of these eigenvalues will be product of that, right? Maximum will be the maximum of this product. So then it's clear. So the norm of T1 tensor T2 equal to norm T1 times norm T2. So for finite dimensional, this is clear. A finite dimensional, when T1, T2 self-adjoint, this is clear. So for infinite dimensional, so if H1, H2, infinite dimension, and T1, T2 arbitrary, then what do you want to do? And you want to consider, you want to consider, so to talk about the norm of T1 tensor T2, you want to consider unit vectors in H1 tensor H2. You can take the maximum of the norm on the unit vectors, right? T of active. So you take summation lambda I xi tensor yi. Okay, let's say take something like this in H1 tensor H2. This is you want to act this T1 tensor T2 on this. Okay. Now T1 tensor T2 acting on summation lambda I finite sum. One thing lambda I xi tensor yi. Okay. Norm square. You take the norm square. This will be equal to, you just write it and compute it. This will be just I take the summation out. I mean, it's an norm square, which you write it as inner product of this. So summation ij lambda I lambda j bar. Okay. And then T1 xi xj. Okay. And T2 yi yj, right? This is how it will be. This is how it will be, right? Okay. Now let you take, I mean, if you just compute this, this is how it will be. This is just the inner product of this element with itself. Okay. Sorry, there will be a T1. T1. There will be T1, T2. Now let you to take P1 to be the projection from H1 to the span of this whatever x1 up to xn. Okay. And P2 is the projection from H2 to span of this y1 up to yn. Yes, I mean, then this will be a finite rank projection. The range is finite dimensional. So this whatever you have here equal to summation ij lambda I lambda j bar. Okay. So P T1 star, you can insert a P here because xj are in that range, you know, P1 is the span of these things. Okay, xj's are in that. So I can insert a P here, I can insert a P here. So which is just P T1 star T2 T1 star P1 star T1, sorry, P Xi Xj. It will look like this. Okay, times P1. So P2 T2 star T2 P Yi Yj. Okay. Now this will be less than or equal to norm of P1 T1 star T2 P1 times norm of, let me tell you why. T2 star T2 T1 star T1 T2 star T2 times norm of the summation lambda I xi tensor yi whole square. That is because you can see now you have got the P here. So now you are only working with this kind of operators. You call this as some SI. These are all finite rank operators. It's only on finite dimensional thing. Now you take the sum inside or whatever. Now you have this inequality, no? You have this inequality that summation, I mean, for any T xi xi is less than or equal to norm T times norm xi square. Now, if you take all this sum, now you are work with only this Hilbert space, H1, this projection, P1H tensor P2H on that Hilbert space. On that Hilbert space, you have these operators. P1, P of T1 star T2 P tensor P of T2 star T2 P on PH1 tensor PH2. Work on this. Now you know that this satisfies that inequality. And this, when you take the corresponding norm, it's exactly this. This is exactly equal to, exactly less than this. So from all these things, it will follow that. I mean, this I leave it as exercise. Okay, this is very simple computation with norm. Okay, so from all these things, it follows that norm T1 tensor T2, whatever we define, is less than or equal to norm T1 tensor norm T2. That's what it follows. Now you want to get norm is attained somewhere. Okay, so for that, there exists a vector xi in H1 with norm xi equal to 1 and T xi is greater than or equal to norm T1 norm T1 minus epsilon, right? Because the supremum is attained here. So, I mean, supremum of this kind of norm is this. Okay. Similarly, there exists a eta in H2 such that norm of T2 eta is greater than or equal to norm of T2 minus epsilon. Okay. Now, if you would take a T1 tensor T2 of xi tensor eta, that norm will be greater than norm T1 T norm, I mean, the product of that square. So you can show that this will be, I mean, this norm of T1 tensor T2 xi tensor xi2 is greater than this. Okay. I leave it as an exercise. Okay. Please do it. Okay. I mean, this is the idea. Norm of T1 tensor T2 is equal to norm of T1 times norm of T2. For that, you can approximate this by T1 xi. You can approximate T2 by this. You can approximate T1 tensor T2 xi tensor. You can approximate norm of T1 tensor T2 by T1 tensor T2 acting on xi tensor eta. But that is normal. That's all. Use the epsilon correctly and you will get it. Okay. Let me not do that. So these things imply that you can define T1 tensor T2. It's well defined. It's a nice map. It's defined on tensor Hilbert space. And that does the product of the norm. That's all. And there are many things as exercise you can, I mean, I don't want to go through all that. If you take T1 tensor T2, okay, and you have a lambda here, that is same as T1 tensor lambda T2, because it is satisfied by the product. You can see that these two are equal. And you can, so you can unambiguously write the take the lambda out, lambda times T1 tensor T2. Okay. And similarly, if you fix one of them, you can sum that. If you fix this, you can sum in the second product. If you fix one of them, so those things should be clear. Okay. So you verify all these things. You get yourself familiarized with this. Okay. So there's nothing to prove for me. You have to familiarize yourself. So for that's all for tensor product. We will get to tensor product again in the next class. So since I have time, I will do something else. I want to, so okay. One more thing is there is something called amplification. So if you have H1, H1, H2, okay, then you can talk about, you define B of H1, tensor 1. By this, we define all those T tensor 1, where T is of H1. Okay, and this whole thing is contained in B of H1 tensor H2. You have a Hilbert space H1, H2. When you have H1 tensor H2, on B of H1 tensor H2, you can embed B of H1. Okay, so B of H1 tensor 1 is, by definition, it is this. All those T tensor 1. Okay, so this is a subalgebra. This is the representation of this. One thing you should remember, even some of this may be even finite dimensional, but T tensor 1 will not be finite dimensional, right? Because 1 is an infinite dimension. So this will not, you think about it. If you take a finite, this is a different on an infinite dimension, but one, this is an amplification. This is something like, so see, the product is a sum repeated many times, right? Similarly, H1 tensor H2, if H2, you can write it as direct sum of CEI, where EI is an orthonormal basis, okay? Right? Infinity. If you take any vector, infinite dimensional vector space, EI is an orthonormal basis, then this is what is this, right? Okay, this is clear, no? So you can write H1 tensor H2 as direct sum of H1 repeated I equal to 1, 2, where H1 tensor CEI if you want. But if you tensor with one dimensional thing, you will get the same thing. I mean, C is like an identity in the tensor category. I mean, say the vector space C. So if you tensor with C, you will get H1 itself. I mean, it's actually different Hilbert space as sitting inside this. But as a Hilbert space, it's just the same thing. You can identify with this, C tensor. It will be Xi tensor something, one of them. So the lambda doesn't matter here, right? This lambda, you can take it inside. And this is just, it's like this. Okay. Xi tensor E1. Okay. So why am I saying this? So if you have a even finite dimensional thing, this is T tensor 1 is something like T repeated many times. It's like a diagonal. You have already seen this in the von Neumann double commutative theorem proof. There we used, if you have a Hilbert space, M is embedded in B of H, then we took H direct sum, H, N times, right? Then we defined on that and we did something. That is nothing but, if you use the language, that is just nothing but H tensor Cn. So it is that M is represented as M tensor 1. Like, okay, like V of H tensor 1, if you have a M contained in this, you can write M tensor 1 also. Okay, this is just T tensor 1, where T is in M. Okay, you can define this. You can amplify, I mean, you can represent anything, amplify this. So whatever we did was an amplification. This is exactly the von Neumann double commutative theorem, whatever we did. We used the proof by taking direct sum. That is just the tensor product. Okay? I mean, tensoring with a finite dimension, with Cn. So that's what we did. So this is amplification, all that. So finally, I want to prove something about von Neumann algebra and then stop, because I have time. Or if you are tired, I can stop. Is this too much to take? Or you can do more. But it may not finish in 15 minutes. Let's see. I will try to finish it in 15 minutes. Okay. It is just a very simple theorem, which I want to prove today, so that it will be used to classify type 1 algebra in the next class. Okay, let's forget about tensor products. Return to von Neumann algebras. Okay. So let M be von Neumann algebra. And you take a projection P in M, okay, this position. Okay. Then you define PMP, so this definition, okay, which is all those PXP. Okay. where H is equal. You are hitting with a projection on both sides. Now this will be an operator. You consider this as B of PH. Okay. You can do it now. You have a H, you projection P, that will give a subspace. Okay, now you hit it like this, that will give an operator on PH. Okay, so these are all operators on PH. So this is a von Neumann algebra on this Hilbert space PH. I mean, this is not a, we are going to prove that it's a von Neumann. That's the part. That's the statement to this. Okay. Similarly, for M commutant, you don't need to take PM. I mean, you don't, because it's commutes. P is in M, so it commutes. Okay. This is all those things which are X prime P, where X prime is in M commutant. Okay. This is also contained in B of PH. Okay. Then both PMP and M prime P are von Neumann algebras, okay, on this Hilbert space, and they are commutant of each other. Yeah. Okay, that's all. So that is the statement. You can have a projection and hit it. I mean, if P is in M, you have to take PMP, hit it both sides. And if it's in the commutant, you have to hit it on one side. And you get a not sub von Neumann algebra. It is not sub von Neumann algebra of that. This is on a different inverse. Von Neumann subalgebra, whenever we mean yes, von Neumann algebra sitting inside another sub identity should be same. Okay, so here the identity is P in that, right? Both this PMP and MP, M prime P, the identity is P. So this is not a von Neumann subalgebra of this. When we say subalgebra, identity should be same. Okay, so this is sitting, this is a different von Neumann algebra, sitting inside the PH, different inverse. Huh? Huh?
Not like the distinction that like subalgebra having requirement
for von Neumann algebra, maybe sister algebra, something. It depends on how what they agree, what they.
Yeah, I guess like I was looking at different approach.
Possibly,
Yeah.
but von Neumann algebra, it will not be nice if you take have to work with different identity. Okay? So here we want identity the same. At least for von Neumann algebra, when we say yeah. So for that you can do something. Okay, that will work. But for Neumann algebra, whenever we say something is included, the identity should be same. The identity should be there. C-star algebra, you may have different identity. For a subalgebra and all that you can work. That's different. Yeah, the identity should be same. So that's on the same Hilbert space. So proof. We just have to be very careful. That's all. Okay. So the proof is not difficult. It is just we have to be careful. So what do we have? We have a von Neumann algebra on B of H. We have a projection in that. So then we want to talk about PMP and M prime P. That's all. We just have to be, I mean, it looks trivial also, the statement, but we have to verify something. Okay? The von Neumann algebra means we have to verify this commutant equal to this. If we verify they are von Neumann algebra, because they are commutant of something is a von Neumann algebra. If you have commutant of something, then that is the double commutant of that. So that's a von Neumann algebra. So you have to prove that only. So first, if you have a, so let's see, one is included in the other. So if you have a X prime P in M prime P, and if you have a XP P in PMP, okay, this is just a notation, then it is clear that PXP X prime P, if you want, you can consider that on the Hilbert space. Okay, then I mean that doesn't matter. You can take this X prime because all this is commute. You can take it here. You can take this P with this, and you can extract it. You can take another P from there. This is also equal to X prime P, P X P. This is clear. This relationship is clear. This relationship you can verify on H. It will hold. If you consider this as an operator on PH, it will hold that also. If you want to convince yourself something commutes on the big Hilbert space, then you are just saying this block commutes. That will commute, of course, right? Okay, both are same. Okay, you are just working with the block there. Okay, so this implies PMP is contained in M prime P commutator. That's what this means. Okay? If this is commutes with this, so this is contained in the commutator. Similarly, M prime P is contained in PMP commutator. That's what this says. Of course, both the same statement. Both the same statement. I'm just saying. We want to show it's equal. So we need to prove, we only need to prove PMP contains MP commutator and M prime P contains PMP commutator. That we have to prove. Okay. So then it will be equal, and they are, of course, they are phenomenal. Okay. Okay. So we want to prove this. Say 1. To prove 1, so we want to prove that, yeah, that state x prime p in MP. No, let x be in B of PH. Okay. I mean, we want to prove this. Something here should be here. That's what we want to prove, right? Something here means what? It commutes with MP. So you take a x in B of PH, okay, or x delta if you want. Okay, doesn't matter. Okay, x maybe x. Okay, x delta. That x delta is in B of PH. Okay, such that x delta commutes with this Px prime equal to Px prime. X prime B doesn't matter. X delta. Okay. Then we want to prove it is here PMP. Okay, then want to prove there exists a x in M such that PXP is equal to x delta, right? Is that statement clear? We want to prove this is contained in this. So suppose an element in B of PH commutes with this, then it should be here. That means you have to produce a x here, such that PXP equal to this. Okay. So that is the statement. So you take that element itself, okay, or you have x delta defined on this, okay. So you take, you want to define an operator on H. So you first hit it by P, then you take the x delta, okay. Take, this is x, this is in B of H, right? I mean, this is just a notation, you should understand. You want to define an operator on B of H. So for that, you first, x is just an operator on B of PH, which commutes with that. Okay. So I take x delta and I apply P before that. So that will give an operator on B of H. Okay. Now we want to show that this x is actually in M. No. We want to show that x is actually in M and PXP is x delta. PXP x delta is clear because x delta is going to leave this in PH invariant. Right? PXP equal, yeah, PXP equal to what am I saying? Px tilde P. PXB equal to x tilde, I want to say. What do you want to say? I want to say that PXP equal to x tilde, right? I want to say PXP equal to x tilde on PH, right? That is clear, no? X tilde is an operator on PH. Now, x is nothing but, I mean, it's clear. If you want, x tilde is an operator here, something here, 0, 0, 0. Okay. X tilde as an operator. Now you are saying that you are multiplying by P. So you will only get this. I mean, this is X tilde. This star is X tilde. X is nothing but this, right? Okay. Now, if you take P, you will get only star. Okay, so this is clear. There is really nothing. You would have to only carefully, you have to just think carefully. So this is clear. Now I have to show that this actually commutes with Px, Bx prime. Okay. What do I have to show? I have to show that this is in X is in M. Yeah. So I want the other way. I want to say that X is also equal to Px tilde. That's what I want. This is also true. It doesn't matter which way you write. X tilde, it's here, sitting here. Okay. Now you are applying P with something. So that will become this. Okay. Now X tilde, if you apply P here, I mean, this is our X. If you apply P here, again, that will be same as this. So X equal to Px tilde is also true. Okay. It is just how you understand this. That's all. Okay. This is true. Now you have to verify that this X commutes with M prime. So it will be in M. We want to show that to prove X is in M. Okay. We show that it commutes with X prime. We compute Xx prime equal to P X tilde P X prime. Okay. Which is equal to P X tilde P. We can extract a P, doesn't matter, X prime. Okay. That is equal to P. We can bring it past here because it commutes all these things. I mean, you can, it's clear that you can bring it here, which is equal to X prime. You can take the P again here, which is equal to P times X times X. It's easy to check. Okay. You just write down carefully, it will be clear. Okay. It is just that there is no problem with that. Okay. I mean, to get a X, you just see the point is P is in M. If X is in M, you are only going to take this block as this operator on that. If the block is in the PMP, then you can, I mean, that block is given by something from there. You can take that operator itself. That will, if you take X tilde or something here, then this will be in M. That's what this says, right? This will commute with that. That will be clear. Okay. The other one is not easy. For that, we need something. So now to prove the other one, which is P MP commutant is PMP commutant is contained in M prime P. Okay. I forgot to say two things. These are the two remarks you should remember. Because we haven't completely proved the spectral theorem for normal operators, but I think that's not needed. So if you have any C-star algebra, okay, then A is equal to span of unitaries. You don't need to take closures. If you have M is a one-dimensional algebra, unitaries in A. Okay, and you take unitaries in A and the span of that. M is a one-dimensional algebra, then M is equal to, you take all projections in M, you take the span, take the closure, the strong topology. These two are clear because if X is in A, okay, then X equal to X1 plus I X2 for Hilbert joint. Okay. So it's enough to show that, I mean, you want to show that A is generated by unitaries. You want to show, right, any X in A as span of unitaries. It's a sum of 4 unitaries. Okay. So it's enough, and any x is the x1 plus ix2 for self-adjoint. So enough to verify for self-adjoint. And you can multiply that by a constant and assume that norm of x is less than or equal to 1 and x is self-adjoint. Okay. Then x is self-adjoint, then you have functional calculus. Okay, you consider this function. I mean, see, x is self-adjoint less than or equal to 1. It's like a real function. Any real function less than or equal to 1, you can call about, I mean, consider it as a cos t or something, right? Its value will be. So, I mean, this is just f of t going to t is that function. You call it as cos t. Okay, so I mean, you just have to write it like this. X is equal to f of t I f of t bar, right? Is that right? Where f of t equal to t plus I square root of 1 minus t square. Sorry. F plus f bar by 2. I mean, let me write f of x plus f of f bar f of x star by 2, where f of t equal to t plus I into square root of 1 minus t square. This f of t equal to t plus I into 1 minus t square, this has modulus 1. This is cos t plus I sin t. You can take the modulus, which is equal to 1. So this is a unitary. This f of x is unitary. And f of x plus f star x by 2 is x. Okay, the imaginary part will go away and you get x. So any x can be written as sum of 2 unitaries. I mean, we are only using the spectral theorem for self-adjoint operator. And similarly, any von Neumann algebra M, von Neumann algebra generated by an element x is just, you know, that is pi tilde of that, no? Von Neumann algebra generated by x and 1, I mean x, is equal to pi tilde of that L infinity, whatever, that representation corresponding to that x. That will have all those indicator functions, and you can, anything can be approximated by indicator functions, so anything can be approximated by projection in strong topology. So from that, this follows. M is a von Neumann algebra, then span of all projections. Okay, so this is some. So now coming back to this. Now, so let me remind you what we are doing. We have a von Neumann algebra M on B of H, M and M commutant. We took a projection P in M, and we hit the M by P on both sides, P and P, and the commutant on one side. It's enough to hit it on one side, so P M prime P. And we want to prove this. We have proved all the other inclusion. We want to prove this is equal to this. We have proved all the other inclusion. We want to prove this. P and P prime is contained in M prime P. To prove that they are von Neumann algebras and they are commutant of each other. That's what we want to prove. We have to prove this. To prove this, enough to prove unitaries. I mean, I have this notation. Okay. Unitaries in that. Okay. Unitaries in that is contained in M prime P. Because unitaries are there, then the linear combination will be there. So it's enough to prove unitaries are here. So let us take a U in P M P commutant, a unitary. Okay. We want to prove that this U is some x prime P. We want to get a big unitary, want a U tilde in M prime such that this is contained in this you want to prove, such that U equal to U tilde P. That's what we want, right? We want to show that this is contained in this. So it's enough to show unitaries in here is contained here. Okay. So we took an element here. That is, it commutes with PMP. That's what it means. Right. Huh? No, it's also a C-star algebra. You can work with projection. Whichever is convenient, you use that. That's all. It's also C-star algebra. Okay. So if projections are convenient, you can use that. Unitaries is you can verify the inner product and do something, no? So that is a nice thing, okay? So you have a unitary here, okay? Now you want to show that that unitary is in this, and it's a unitary which commutes with PMP, okay? So, okay. So you want to define a U tilde such that this happens, okay? So let you have a different H naught equal to span closure of M. You have this Hilbert space PH. Okay. PH is contained in H, of course, right? PH is a subspace of this. Act M on PH and you get a bigger Hilbert space. Okay, then take the span closure. You call that as H naught. Okay. On that, define U tilde on the span you want to define. Okay. Summation Mi xi, where Mi is in M, xi is in H, PH. Okay. You define that to be summation Mi U xi. Okay, I will write it there again. I will recall everything. I can do it again. We want to prove we have some P, M, P, commuton. We want to prove that this is contained in M prime. Okay. Now we take a U here, which is unitary. Okay. Then we took our H naught to be span closure of M PH contained in. Okay. Now, and Q be the projection. It's Q from H to H naught projection. And to define U tilde on H naught, of course, on H, I'm not H naught, U tilde, let's define it on the span. Summation Mi xi equal to summation Mi U xi. Okay? For Mi in M, xi. This is well defined. Let's not worry about well defined because we are going to define, we are going to check it preserves the inner product. Then we don't need to even verify well defined. Okay. Now you have summation Mi xi, summation Ni xi. Okay. U tilde acting on that, U tilde acting on that. You will get U here, you will get U here. That is equal to summation Mi summation Mi it is in PMP commuton. Yeah. Now, why does it preserve the inner product? Summation Mi. So, sorry. We can take this as this, yeah. Now this is equal to summation Ij. Okay. You have that Mi and other thing. You will get a U here, right? When you apply U tilde, that is how you get a U here. Okay. I write it the whole thing, which is equal to U star Mi, Ni star Mi, Nj star, sorry, Nj star Mi, U xi eta j. This is xj. Eta j, eta, sorry. Ni eta j. Okay, this is N, this is eta j. So Uy N psi I eta j. I will get a U here, I will get a U here. Okay. Then I take this Ni, which is an element of the phenomenon, Ni star here. So, and then you have a U here, that will be U star. That's what I have written. U star, Ni, Nj, Mi, U. But then U commutes with this, I mean, on this, if you want, you can take a P here, and it commutes with the PMP, right? It commutes with the PMP. Okay. So if you want, you can put a P here, and P will not commute with this. So I want to take this U there. U, Ni, Mj star. There is P coming here. U doesn't commute with U commutes with PMP, not with this. So I need a P here. I can take a P also, sorry. I can put a P here. If you want, I mean, it doesn't matter, it's P's again. I can put a P here, and then U will be here. But then it commutes with here, P. So you can take the U past this P, doesn't matter. I am saying we will get this. Let's just write it. Equal to summation over Ij inner product. I will write it and then explain, okay? So summation of this, then U P Ni star Mi. I'm just verifying that this U tilde is a unitary. Okay? This is equal to summation over I and j inner product. I can put a eta I, eta j. Okay? I can put a P here because they are anyway in pH. I can put a P here. And this is equal to U star P N J star Mi P then Xi eta j. Okay. If you want, you will have a U star here and then P here because U is a unitary on pH. Okay, so whether you put a P here, B here, it doesn't matter. Okay, so this is okay. Okay, now U commutes with this. I'm sorry, there is another U here. U Xi eta j. Okay. Sorry, there is another U. There is U here. Now this U, we are assuming U is in this, commutant of this. Now U commutes with this. So you can take this U past all these things and U star U is identity. Now this is equal to summation Ij. You will not get a U. Eta j, it's not nj star Mi, and P is not there anymore. If you want eta j. Okay. Now you can wrap up, get the sum again. That will be the same as sum. Exercise. Okay. U tilde preserves inner product. Okay. That's what I have verified. Okay. So U tilde extends to unitary. On QH, which is our H naught. Okay. Now define now verify now. So see, now this H naught is left invariant by M. H naught is defined as span of MPH. If you take a element in M, it will come here, it will go inside this. Okay, so H naught is invariant under M and invariant under M prime because already pH itself is invariant under M prime. So if you have a M prime, something commutes with it will go past this and it will leave this invariant. Okay, and M prime also. Okay, so this H naught is left invariant by M and M prime. So this projection Q is in M intersection M prime. Okay. Now you define You call that U, no? U naught equal to U tilde Q. Now this U tilde Q will commute with then M prime. Because Q is commutes with M and U tilde, I mean, it is in that, I mean, you can see, okay, verify, okay, etc. Just verify. I mean, okay, you want to, okay, let's check it. U tilde Q, okay. You want to verify U tilde Q commutes with M, something in M. So times M. So you have to only verify it on, you have to verify enough to verify, enough to prove U tilde M equal to M U tilde on QH, on this H naught. Okay. On H naught, these vectors look like this. Okay. So now U tilde M on summation Mi xi equal to summation Mi U xi, which is equal to M times U of summation Mi xi. Yes. That is how you if you remember, that's how U tilde is. U tilde acting on summation Mi is U comes here. Okay. Okay. If you are getting confused, I will repeat it again. Okay. That is how we define this U. U tilde acting on summation Mi xi is the Mi U xi. Okay. So if you have a M here, this M will come here, but U tilde will appear here. Similarly, if we have a M times U, then M will here, this will go here. So it comes clearly U tilde M is equal to M U tilde on Q, the Hilbert space H naught. But Q already commutes with M prime. So U tilde is in, so whatever the U naught is in M prime. Okay. It will follow U naught is in M prime. And you can see that U naught, when you hit it with P, you get that U by definition. Shall I mean, by definition, it will follow. If you are not understood, oh my God, I completely forgot to. So I'm sorry, you cannot. Shall I go through the whole thing again? If you want to watch the video, you will not be able to see because that was focusing there. So maybe I will explain it again. I will just orally say. We want to prove that PMP concomitant is contained in M prime P. That's what we want to prove. Okay. It's enough to prove. You take a unitary here and prove that that is here. So you take a unitary here. Okay. So you want to prove that is here means you have to produce something here times P, which is equal to this U. That's what you have to prove. So for that, I take this H naught to be span of this MPH. Okay, closure. So any element here will look like summation Mi xi. On that, I define U tilde like this, Mi U xi. Okay. Then I verify this inner product, which is preserved. Okay. Because you can write it like this, U star P and Ni star Nj star Mi P U A. You can write it like this. You can bring a P and other thing if you do the calculation. So because of that, it preserves the inner product. Okay. So because it preserves the inner product on the dense subspace, I mean on the total subset, whatever. So because of that, it will extend to a unitary on H naught. Now you define your U to be Q times that. You have a Q times U tilde. I mean U tilde times Q. First you project it onto that H naught, then apply U tilde. Now because of the very same equation, this U naught will commute with anything in M. So U tilde is in M prime. Now if you hit it U tilde with P, okay, if you hit it with P, then you will only get xi and you will get only U. Okay. U tilde acting on P is just U. There is no Mi, all these things, just xi. Mi is identity. So this is just U. So it's clear. So we have proved that U naught, whatever, U naught P is equal to U, the original U. Okay. That's what we want to prove. So unfortunately, the camera was there. But I hope it will go through. If you are not clear, you ask me. Okay. But it is better to go through this. Okay. I will make a corollary and stop. Sorry. Just a corollary. I pressed it, I think that moron didn't turn. The corollary. If m is a factor, then the q defined here, then the q which is in the center, q is identity. Okay. So I'm saying that x prime going to x prime p is a weakly continuous, which is of course clear because this map itself is weakly continuous. Weakly continuous star isomorphism of m prime onto m prime p. M prime p and they are isomorphic. Okay. So m is a factor means m prime is also a factor, of course. So then this is a star isomorphism on that. Okay. Why is it an isomorphism? Then because q is equal to 1. No, not yeah. We have to prove it. Sorry, we have to prove that this is an isomorphism. Okay, and okay, let's prove this. Prove. So all we have to prove, it's clearly x prime going to x prime p is on to weakly, is on to clear, and it is clearly a weakly continuous. All we have to prove that it is injective. Okay, only need to prove x prime going to x prime p is injective. Okay. So if x prime p equals 0, okay, so then x prime acting on summation mi xi is equal to summation mi x prime xi. Okay. X prime on p, x prime p is 0. So this is equal to 0. But then summation mi xi, q equal to 1 means summation mi xi, this is dense here, okay, where mi is in m, xi is in h, xi is in ph, is dense. So x prime is 0. I'm saying that if x prime p is 0, x prime is 0. That is because if x prime is 0 on ph, then this kind of elements are dense in H because q equal to 1 when it is factor. So x prime equal to 0. So x prime going to x prime p is a weakly continuous isomorphism. Okay. So corollary to that is if m is factor, m prime is factor, then m prime p is a factor. Okay. Then its comitant is p mp. This is also a factor. Okay, that's what I want to say. Stop.